record. Cool.
Okay.
Yeah. All right. You're welcome to share now. We will be
It says it's disabled still.
Oh, does it?
Yeah.
That's sharing options. All participants. You should be able to now.
Okay. Yeah. So basically,
yeah.
Okay.
That's good.
So I just started off with like the background for like people who are completely new, but you would know this already.
Yeah, like I've seen it before. I just need to refresh.
Yeah, just how to represent a state, and then what the Hadamard gate does, the superposition.
Exactly.
This is just a phase shift.
Right.
If you want to go in the deep mathematics, is the C naught gate.
Yep.
And this is just what entanglement does. You apply an H gate to a 2 qubits, and then, you apply an H gate to 1, and then you C naught them both, and then you have this entangled state.
The tensor product of the 2 states, right?
Yeah. So the entire problem, right? The problem statement is that you have some oracle that either gives a given 2 inputs, the output, which is your Y, I guess, input is X. Your output can either be a constant 0 or 1, or it is a balanced oracle, meaning that it either applies the identity or not gate to the X to get the Y.
I think the way you drew the diagram, I'm not sure. So you're drawing it for a 2 qubit system, right? So I think the first one needs to be initialized as 0, but the second one needs to be initialized as 1.
Okay.
Yeah. That's what I remembered reading on the Qiskit website. Let me just double check. Give me a second.
Oh, okay. I know there's multiple ways to come at this, and yeah, I did remember on the Qiskit it did say 0, 1.
Yeah. So see here, give me a second. Can you stop sharing? I'll share mine.
Yeah.
All right. Cool. Yeah. So see over here, it says so we have 2 registers over here in this case, and this can be a how many qubit oracle that we choose it to be, and 1 qubit. So this is our oops, no, I did not mean to do that. Give me a sec. Okay, yeah. So so this is a how many qubit oracle, and we have a second register. So this is 1 register, and our second register is just a single qubit that is initialized to 1.
Okay.
Yeah. So
I don't know why then the math works. I thought, okay. I mean, we'll probably figure out wherever I went wrong then.
Yeah, we'll probably figure it out in time.
Okay. So I guess the first thing is we apply a Hadamard onto these 2 qubits. I'm just saying it's going to be 2 for now. So at this beginning stage, we have qubit 0 and qubit 1 are both 1s.
Yep.
Then once you have this, in the B stage, you have 2 superpositions, which then expands out to this
whole thing.
Yeah. And from here to go to this step 3, this is where you apply the oracle, which is denoted by the F function.
Yes.
And the basically this first qubit, or the index 1 qubit, that is what determines if f of x is inverted or not, since it is a controlled NOT operation.
I see, yeah.
So for the first one, it's 0.
Oh, sorry. I just want to say one thing real quick. You are doing a terrific job taking notes over here. I think next semester or whatever, you're probably going to be like an education lead or something, because this is excellent.
Oh, thank you.
Yeah, but anyway, continue. I'm sorry for
no worries. But thank you for that. So let's see. here we have, if we go step by step, we have this expands
Mhm.
to 0, and
Yep.
the insides are just going to both be x. And
Right.
then since this control qubit is a 0, nothing gets inverted. Then for this one, put a 1, and you still put a 1 in here, but it says a 0, no inversion. Same thing
Okay.
here, except now there is an inversion. Same thing here, now it's an inversion.
Okay.
And that is basically it. Now once we've applied our oracle and C naught, now we can see that if the function is actually constant, meaning that this applies true,
Mhm.
using some algebra, you can just substitute in these values and factor, and you get this right here, this top.
Yep. Yep.
And otherwise, if it's balanced, this equation holds true, and you can factor it out to this.
Okay.
And once you apply the Hadamard one more time, if it's constant, this is the function, this is the expression that'll arise.
Yeah.
And yeah, obviously, if you were more people, I would be like going in depth into the math. But one more thing is if it's balanced and it goes into this, and this is mainly where we can see the answer, how the qubit at index 0 becomes either a 1 if it's constant and 0 if it's balanced.
I
And
see.
we've done that in one query instead of a classical algorithm. We'll do it in 2.
Yeah, and this is where the quantum comes into play because we can now have we can decrease the number of queries that we have to this oracle, and that's why this provides
Exactly.
a speed up. Okay, yeah, I see.
Exactly. Yeah.
I see. All right, that's could you actually go up a bit? I would like to go a
Yeah.
bit more in depth in the math if you're okay with that.
Yeah. Oh, of course. Yeah.
So I see that you have your psi sub b state over here, and the way,
Yes.
yeah, and the way that's going to the underneath part. Can you
Mhm.
explain how you got there, actually?
So here I would probably expand this into, or okay, instead of writing it like this,
Yeah.
uh, I could probably just write it as 2 kets that are in the superposition state. So kind of like what we've done in FRI, where we would write
Yeah.
it as, since these are 1s, they would be negative 1s, right? So
Yeah.
like this.
Hmm.
Um, and we would be doing the tensor product since it's 2 qubits.
Okay.
And essentially, all this is doing, this set B, another way to
Mhm.
understand it is you're just establishing a superposition of all possible values, all possible combinations.
I see.
So it's just 0, 0, 1, 0, 0, 1, and 1, 1.
Okay.
And this is the,
Oh. Oh. Okay. Yeah, I see what you're
yeah.
doing.
And instead of 1 over root 2, it's 1 over 2 since you have the
Yep.
4 terms.
That's how the
Yeah,
tensor product works.
I feel like this is the easiest, like jumping to this step is much easier if you see it as just a combination of all of the possible values.
Yeah. Yeah. That starts making a lot more sense.
Okay, then I'll just
Okay. No, actually, yeah, yeah, yeah. Keep that.
I'll
So,
highlight this.
how did you get to psi sub c now? So I see
Psi
how
sub
you
C. Okay.
yeah. So how did you put the function in instead? Is the first qubit acting as the oracle,
So okay.
or the
Uh
qubit at position 1? Sorry.
yeah, okay. Yes, that's right. The qubit at the index 1, so this qubit sub 1,
Yeah.
in this case, that is going to be the control qubit, sorry. And I
Okay.
get it how this is a bit weird how you're replacing that with the answer, right?
Yeah.
You're calculating the answer, but then replacing.
Mhm.
But that's how it's done. So
Mm.
you just copy this in it first qubit down. This is just your X value. This is your input, and then this is the controlled bit, and this is what you're acting on basically. The 0th index bit.
I see.
So
Okay.
that's why I know this upper representation might be weird for some people, how it's like 0 0 1 0 0 1 then 1 1,
Okay.
but it allows us to see clearly how these first two, since their
Mm.
control bits are 0, you're
Mhm.
not doing any inversion, but for the second
Mm.
two it's 1, so you will do an inversion.
Okay. I see what you mean. Yeah, that starts making more sense.
Okay.
I see. Yeah. Okay. So, let's see what you got going on over there. Oh, I think in your if balanced solution, you have your f sub zero, you have your f of 0 sub 1. I think you forgot like the bracket at the end over there.
Oh, you're right. What's this?
Just like clean
Thank you.
notation.
Yeah.
But all right. Yeah, things make sense over there. And okay, yeah, things start. Yeah, okay, so this starts adding up. I see where this is all coming from. I see.
Yeah, I think also another part that might be a little bit tricky is going from here to here.
Yeah, yeah, you're probably right.
So I mean we can work that out right now.
Yeah, yeah, let's do that.
Okay, so we got to here from just substitution, or no, from here we just substituted the values to get and factor to get this. And
Yeah.
applying the H gate. What I'm thinking is, I mean, we can approach this from like using bras and cats,
Mhm.
or we can turn it into like matrices and then do that and then turn those back into bras and cats. That's also another option.
Hmm.
Um, let's see.
Wait, could you repeat your two thoughts one more time? I don't think I caught them really.
Oh, I was saying to go to demonstrate like the transition from these states, from this equation to here, we have to apply the Hadamard gate, right? And
Yeah.
the two different ways we can apply it is by applying it as a, like up here where we applied it and we used just bras and cats and we just went at it like this, or
Yeah.
we demonstrated it using these matrices.
You would know how to do it using browse and catch, right? Or
I think so.
okay.
Yeah.
Hmm.
Oh, I'm so stupid. Yes, I know how to do this in bras and cats. Yeah. Okay, this is gonna be much simpler than we even realize. I've completely forgot this is how simple it is. Okay. If we take this top, I'm just gonna close the screen one more time.
Okay.
My pen was not working. Okay, yeah. Basically, if we take this, right, and we're applying a Hadamard on the 0th, the 0th index. Yeah,
The 0th index qubit.
yeah. So we literally, this side stays the same because
Hmm.
this is the first qubit.
Yes.
But this side, this basically doesn't collapse. It goes back to this one state because that's all this is. This is a superposition of the 0th qubit,
Yes.
right?
Mhm.
Or yeah. So if you apply, and the thing is, if you, to bring something into superposition, you apply a Hadamard gate. Then to bring it out, you apply another one. And that's all this does. It applies one to the first qubit, sorry, 0th qubit, and it brings it back to the 1 state. But this here, if you apply it, it brings it to the 0 state.
Oh, I see.
And this essentially stays the same. We don't really care about this part.
Okay.
It's just
okay.
this factored.
Fair enough. Yeah, I see what you mean. Maybe you should draw like arrows going down towards each of the respective states.
Yeah, that is good. Because these two stay the exact same.
Yep.
One thing interesting though is it's probably just some basic math thing, but this is a 1/2 out here, right?
Yes.
Would it, for a superposition, would it be 1/√2?
That's. I mean, it's a good question. I don't really know. That's interesting.
We know this 1/√2 should be there.
Yeah, because we're taking the tensor product of something.
Yes.
But what goes from that step to the step right after? If f was. I think they should still be the same because we're applying like a mathematical oracle to some. Yeah. It should be the same. I think it should still be 1/2.
Should it still be 1/2? Okay.
Yeah.
So then, does the 1/2? It doesn't go away here, right? Because that seems weird.
But then if you apply the Hadamard gate to that probability, each of those probabilities that you have up there, maybe it would go away. I'm not sure. I have to do the math out. I'll do the math out.
Either way. Okay, either way, even if there's like a 1/√2 in front, would that really matter for this?
I don't think so. I don't think so.
Okay.
But
yeah, I think.
Yeah.
Yeah. So once we get to this step, we're basically, this part collapses to this. Not collapse, sorry. You you apply H gate, it goes from superposition to back to stable state.
Right.
Superposition back to stable, and this is understandable, right? The 0 minus 1 goes to the 1 state. Okay. And I feel like,
that's understandable. Okay. So yeah, these are really good notes, and I think we should keep them for the future.
Okay.
Is it
I
okay?
can make this into a PDF and post it.
Yeah, please do that. And please send it to me so I can put it on like our Box account or something. Speaking of which, I still haven't uploaded last lecture. I'm sitting on my laurels. That's not a good thing. But do we want to look at the IBM website and a way to code this if we want?
Oh yeah. That's definitely
and we could even check, and we can even check like IBM's math to see what they've done.
Oh yeah, perfect.
Okay, I am sharing my whole screen. So let's see over here. So we have, this is the Dutch-Joza algorithm, and if you want to look this up on the Qiskit textbook, it should be chapter 3, section 3.2. So that's there, but if you want to try it out in the quantum lab, that option is also available. So if we want to look at the introduction, this presents the problem. As you said, you're given a hidden Boolean function, f, which takes as input a string of bits and returns either 0 or 1. And the property of the given Boolean function is that it is guaranteed to either be balanced or constant. A constant function returns all zeros or all ones for any input, while a balanced function returns zeros for exactly half of all inputs and ones for exactly the other half. Our task is to determine whether the given function is balanced or constant. So for the classical solution, classically, in the best case, 2 queries to the oracle can determine if the hidden Boolean function.
I don't know. I don't think you're sharing your screen.
Am I not? What the? Could have sworn I was. My fault. Oh my god, I was. Holy crap! Thank you, dude.
No worries.
Oh my god. Okay. So anyway, if you, I'm gonna show again where you can find this on the Qiskit textbook. So if you want to find it over here, it's chapter 3, section 2, and you could open it up in Quantum Lab if you want to try it, but we're gonna look at it in Quantum Lab over. We're gonna look at it in Quantum Lab over here. So we have this whole thing, and we have the classical solution. Classically, in the best case, 2 queries to the oracle can determine if the hidden Boolean function is balanced, and then we'll know the function is balanced as we have obtained the 2 different outputs. In the worst case, if we continue to see the same output for each input we try, we will have to check exactly half of all possible inputs plus 1 in order to be certain that f of x is constant. So that makes sense. Since the total number of possible inputs is 2 to the power n, this implies that we need 2 to the power n minus 1 plus 1 trial inputs to be certain that f of x is constant in the worst case. For example, for a 4-bit string, we checked 8 out of the 16 possible combinations, getting all zeros. It is still possible that the 9th input returns a 1 and f of x is balanced. Probabilistically, this is a very unlikely event. In fact, if we get the same result continually in succession, we can express the probability that the function is constant as a function of k inputs are this expression over here. Realistically, we could opt to truncate our classical algorithm early, say if we were over X% confident. But if we want to be 100% confident, we would need to check this number of inputs. So now we can go into the quantum solution. Using a quantum computer, let me put this over here. So if we want to look at the quantum solution, using a quantum computer, we can solve this problem with 100% confidence after only 1 call to the function, f of x, provided we have the function f implemented as a quantum oracle, which maps the state of x ket and y ket to x ket y y c naught f of x, where this is the addition modulo 2. Below is the generic circuit for the Dutch-Jozsa algorithm. So you have 2 registers in this case. You have this register, which is all initialized to 0, given a number of qubits. And this one is a single, and this register over here is a single qubit initialized to 1. And you put all of this into the unitary, and then you measure the Hadamards again, and you get your output. Now let's go through the steps of this algorithm. Prepare 2 quantum registers. The first is an n-qubit register initialized to 0, and the second is a 1-qubit register initialized to 1. Apply a Hadamard gate to each qubit. And so what that does, like you showed in your math example, was it gives us this expression over here. 1 divided by square root of 2 to the power n plus 1, because that's how many probabilities we're going to have. We can apply this x state over here along with the Hadamard state, 0 ket minus 1 ket. And then we can apply the quantum oracle as you showed over there, and that's our psi sub 2. So we can get this expression over here, f of x minus 1 C naught f of x, 1 C naught plus f of x, and that can actually truncate to this expression over here, since for each x, f of x is either 0 or 1. And at this point, the second single qubit register may be ignored. Apply a Hadamard gate to each qubit in the first register. So applying another Hadamard gives us this expression over here. And finally, where x times y is equal to x naught y naught plus c naught x1 y1 plus c naught, and then we have that all the way up until our number of qubits, and this is the sum of the bitwise product. Measure the first register, and notice that the probability of measuring this is the following, which evaluates to 1 if f sub x is constant, and 0 if f sub x, or if f of x is balanced. And why does this work? So when the oracle is constant, it has no effect up to a global phase on the input qubits, and the quantum states before and after querying the oracle are the same. Since the H gate has its own inverse, in step 4, we reverse step 2 to obtain the initial quantum state in the first register. So after the unitary, so we see over here that we have a single 1 qubit, and when we apply the Hadamard, we get this number of possibilities, and after we apply the unitary, we see that we have this number of probabilities over here, and this equates to what it did before. And so if we have a balanced oracle after step 2, our input register is an equal superposition of all states in the computational phases. When the oracle is balanced, phase kickback adds a negative phase to exactly half the states. So half the states will have -1 and the other will have +1. The quantum state after querying the oracle is orthogonal to the quantum state before querying the oracle. Thus, in step 4, when applying the H gates, we must end up with a quantum state that is orthogonal to this. This means we should never measure the all zero state. So now we can go on to a worked example. I think a worked example is particularly helpful. Let's go through a specific example for a 2-bit balanced function. Consider a 2-bit function such that f of 0, 0 is 0, f of 0, 1 is 1, f of 1, 0 is 1, and f of 1, 1 is 0. The corresponding phase oracle of this 2-bit or else, I don't know if they misspelled that or whatever, is u sub f of x sub 1 and x sub 0, which is equal to -1 to the power, or to the tensor product, f of x sub 1 and x sub 0, and we apply that to the phase, or to the ket x. We will now check if this oracle works as expected by taking an example state. This is our state over here. We initialize these both to zeros. So realistically, I think what you had was correct in your notes, Sarvesh, and this really just depends on what we initialize it to. It doesn't necessarily have to be 0 and 0. It can be just whatever we initialize it to.
Okay.
I think that's what it means. The first register of 2 qubits is initialized to 0 and 0. The second is initialized to 1. Note that we are using subscript 0, 1, and 2 to index the qubits. A subscript of 0, 1 indicates the state of the register containing qubits 0 and 1. So over here, if we apply the Hadamard on all these states, this is these are all the probabilities, like you said earlier. It is half of all these probabilities, and then we take the tensor product of that with the Hadamard gate applied to 2 qubits. And the oracle of this function can be implemented in this way. So we take 1 over 2, divide by square root of 2 of all of this jazz over here. So we're taking a 3 qubit case. and we have all these different probabilities that can be added. So this is the probability of 0 and 0, and this is our state that we add. This is our 0, 1 probability. This is our 1, 0 probability. And this is our 1, 1 probability. And simplifying this, we get the following. At the very end, we have 1 over square root of 2 of 0 minus 1 over here, and this is for the 0 state, or this for the 0th qubit. Then we have 1 over square root of 2 of 0 minus 1. This is the 1 qubit, and then we have 1 over square root of 2, 0 minus 1. That's the 2 qubit. And we can apply a Hadamard on the first register again to give us this identity. So we have qubit 0 is in the 1 state, qubit 1 is in the 1 state, and qubit 2 is still in the Hadamard state. So if we measure the first 2 qubits, so measuring the first 2 qubits will give us the non-zero state 1, 1, indicating a balanced function. And you can try out similar examples using the widget below. Press the buttons to add H gates and oracles and rerun the cell and or set case equals constant to try out different oracles. So if we want to try out different oracles, we can change this over here. So I think Qiskit gives us a widget to play around with this Dutch Joza oracle, and we can change the size of the oracle or the number of qubits we have, and we can also change it to either be balanced or constant.
Oh, that's perfect. Yeah.
Yeah. So if we have, so if we put, how does this work? Huh. Well, I guess I actually haven't played around with this lab myself. Oh, this is cool. All right. Well, I'll play around with it later, and I think I will upload a separate video that gives like a full in-depth guide to playing with this, because I actually haven't looked at this too much myself. But I guess I'll look at it later. We'll move on to section 3. How much more is there? There's still a bit more, but then, oh wow, this is kind of long. I think after we go over creating quantum oracles, and if we want to do the Qiskit implementation, we can go over each of those, though I really haven't looked much into it. I was not prepared today. This isn't.
Yeah, I didn't realize that they would do like.
Yeah, this is
this
really
much
in
into
depth.
it, yeah.
This is really in depth. I just took like a quick look at the algorithm before this, like the mathematical side, and I was like, oh, okay, cool. But wow, this is really in depth. I'm not gonna lie, out of sheer unpreparedness, I think we'll I think we'd call it a day like right now, because I haven't prepared well enough. But
Yeah, no worries.
I think we should try and go over this again next week, but I'm gonna be much more prepared next time. This is
Okay.
definitely interesting. But I'll stop recording for now.
Okay.